Okay, as promised, we're going to do an example of using the Eff NTU technique. So just to summarize sort of where we've gotten to, we talked about heat exchangers and their configuration, and we talked about this idea of a conductance, which you ought to be able to calculate just based on looking at thermal resistances. And we talked about how if you actually want to solve a heat exchanger problem, you have to do some kind of differential energy balances, which is going to lead you to a solution that in its sort of derived form is not super easy to use. So here, for example, is the solution for a counterflow heat exchanger. But we can put these solutions into a form that is more easy to use if we express these relations in terms of effectiveness, NTU, and capacitance ratio. So when we went through that exercise for these equations for a counterflow heat exchanger, we ended up with this solution right here. And there are equivalent solutions for pretty much any configuration that you can think of, and they're tabulated for you, or you can use those functions in ease that we talked about. So let's use these solutions to do an example. So we had previously talked about this idea of having either indirect or direct transfer heat exchangers. And the example I used for an indirect transfer heat exchanger was something you could use for an energy recovery system in a building. And it was this rotating regenerator wheel. So hopefully you remember this. The idea being you would take cold outside air in the middle of winter, and rather than just dumping it into a furnace and asking the furnace to heat it all the way up to the temperature you want to put it into the room at, you would first preheat it. You'd recover some energy from the warm air that's in the room that has to be exhausted. And in this case, you would do this with this big rotary wheel. And this works great. It's really convenient for new construction where you have the flexibility to locate the ventilation duct right next to the exhaust duct, right? Because then you can run this wheel between them. If you're trying to retrofit old construction, you may not have that option. You may be in a situation where the ventilation duct and the exhaust duct are not right next to each other. And so if that's the situation, then another system that you could consider for energy recovery is what's called a runaround loop. So a runaround loop is basically a loop that consists of two direct transfer heat exchangers. So this is my loop. I have a conventional, probably a cross-flow heat exchanger sitting in my ventilation duct. I run ethylene glycol through that heat exchanger. And then I run it back through using a pump, another heat exchanger, direct transfer heat exchanger that sits in my exhaust duct. So if you think about what's going on here, my ethylene glycol travels through the heat exchanger in my exhaust duct where it warms up because it's being heated by this warm room air that I'm exhausting. This warm ethylene glycol comes over here and goes through the heat exchanger in my ventilation duct, where it transfers air to the cold, heat to the cold outdoor air, right? And then this cold ethylene glycol returns to do it again. So taken at a system level, this is an indirect transfer heat exchanger, right? I'm not directly transferring energy from the warm air to the cold air. Instead, I'm transferring from the warm air to the ethylene glycol, and then at a different time, that ethylene glycol is transferring the energy to the cold air. But it's an indirect transfer heat exchanger that's facilitated by two of these direct transfer heat exchangers. So it's a pretty good place for us to pull an example from. So here's my example. Just to put some numbers on this system, I'm bringing in 5 kilograms per second of outdoor air at some pretty low temperature in the middle of winter. That's going through my ventilation duct. And then I'm exhausting another 5 kilograms per second of indoor air at some comfortable temperature, 25 degrees Celsius, through my exhaust duct, right? So I'm going to now build a runaround loop by putting some kind of a heat exchanger in my exhaust duct and another heat exchanger in my ventilation duct, and plumbing them together with a pump so that ethylene glycol circulates between them. And the mass flow rate of my ethylene glycol is 1 kilogram per second. And we're going to assume that these heat exchangers are cross-flow heat exchangers that look kind of like this. They're big enough that the conductance is 10 kilowatts per Kelvin. This one and this one have the same conductance. They're the same unit. What else? This is a cross-flow heat exchanger. If you look at it on the air side, it's definitely not mixed because I have all these fins. On the ethylene glycol side, it would be mixed because there's nothing inside those tubes to prevent mixing. So we're going to do this one in ease. If I can find my ease file here and open it. So here's the ease file. Up here, I'm just putting in my inputs. So atmospheric pressure, air. These are the two air temperatures. This is the air flow rate. This is the glycol flow rate. The specific heat of the glycol solution is 3.58 kilojoules per kilogram Kelvin, and then the conductance of both of those heat exchangers is 10 kilowatts per Kelvin. So these are my inputs. I'm going to look at the specific heat capacity of air. It's not very temperature dependent, but I'll use the average temperature to get it. Then I'm going to try to analyze these heat exchangers. So let's see. This is, I think, a simulation type of a problem in the sense that I have a heat exchanger and I know its conductance, right? So what I'd really like to be able to do then is compute the NTU for each of these heat exchangers and the capacitance rates. And if I can do that, then I can go off and use the solutions to figure out the effectiveness. So let's see, the capacitance rate of the air is just the mass flow rate of the air times the specific heat capacity of the air. The capacitance rate of the glycol solution is the mass flow rate of the glycol solution times its specific heat capacity. The number of transfer units of either of these two, it doesn't matter since they see the same flows, is the conductance divided by the minimum capacitance rate, so whichever one of these two things is minimum. And then I would go off and just use my library of solutions to get the effectiveness, right? So I'm going to go pick here a cross-flow heat exchanger with one fluid unmixed and one fluid mixed, and that's going to give me the effectiveness. So let's go look at what that looks like. So here's the capacitance rates, this one and this one. I'm picking out the minimum capacitance rate using the min function here. Here's my NTU, and then I go and pull the right function. So this is a cross-flow with one unmixed, and I give it the NTU and the capacitance rates, and it gives me the effectiveness. So the effectiveness of both of those two heat exchangers is about 70%. Okay, so what that says is that both of these two heat exchangers, the ventilation heat exchanger and the exhaust heat exchanger, is exchanging. They're giving me about 70% of the maximum possible performance. The outlet temperature of the minimum capacitance fluid is not going to reach the inlet temperature of the other fluid. There's going to be 70% of the way there. All right, so that's the first part. The next thing I want to do is actually figure out how much should I warm up the air here, right? So the thing I'm probably most interested in is T2, right? What's the rate of heat transfer to my ventilation air? Because that rate of heat transfer is heat transfer I don't have to get in my furnace, right? So that's heat transfer, that's money saved to me. So I need to analyze each of these two things. I have the effectiveness, but I actually don't know any of the ethylene glycol temperatures, right? So what I'm going to do is guess one of these temperatures, T5, and then I can work my way around. And when I get back to here, I'm going to find that the T5 I guessed isn't right, so then I can adjust, right? So that's the typical thing you have to do in any energy system is sort of start someplace, make a guess, and then work your way through the entire cycle and get back to where you started from. And that's how you close up that guess. So here I'm going to assume T5. Once I know T5, that tells me the, I guess this would be the cold fluid inlet temperature. And I know the hot fluid inlet temperature is T3. So the maximum possible rate of heat transfer in this exhaust duct would be the minimum capacitance rate times TH in, which is this 25 degrees Celsius, minus TC in, which is this T5, this cold ethylene glycol temperature. And then I multiply that by the effectiveness to get the actual rate of heat transfer that occurs in this exhaust duct. Once I know that, it's easy to do an energy balance on both sides. So T6 is T5 plus that rate of heat transfer divided by the capacitance rate of the ethylene glycol. T4, so this is my hot exit, T4 is going to be T3 minus the rate of heat transfer divided by the capacitance rate of air, right? So that gets me all the way through the exhaust heat exchanger. So let's look at what that looks like. So I guessed T5 was 10 degrees Celsius. Once I do that, I can calculate Q dot HX, so 37.7 kilowatts. I can calculate T6 and T4. So T6 is, let's put this in Celsius, 20.53 Celsius. So my ethylene glycol goes in at 10. It comes out at 20. That makes sense, right? My warm air temperature is 25, so it didn't get all the way to 25. And if I wanted to, I could look at the, what would it be, T4, I guess. So the air is coming out at 17.5 degrees Celsius. Okay, so that's half the way there. Now I'm going to go look over here at my ventilation duct. So here's my ventilation heat exchanger. I know the cold fluid inlet temperature here is minus 10. Here, the ethylene glycol is actually the hot fluid, right? It's coming in and it's going to warm this stuff up. So the hot fluid inlet temperature is T6. So the rate of heat transfer in the ventilation duct is the effectiveness times the maximum possible heat transfer rate, which is C dot min times TH_in, which is T6, minus TC_in, which is T1, right? So I can look at that and then do an energy balance to get T2. So that's just an energy balance on the air, and an energy balance on the glycol gives me T5, right? So if I solve that, then let's go over here and look. This is my ventilation rate of heat transfer, and this is T2, and this equation would give me T5. So my ventilation heat transfer is 76.7 kilowatts, and T2 is 5.28 Celsius. Once I put this T5 in, obviously I'm going to overconstrain my problem. So at this point, what I'm going to do is update my guess values. And then I'm going to take out my guessed value of T5. And I'm going to put in my actual value of T5 according to this equation. And then all of these equations should solve together to tell me that, T5 is minus 1.96 degrees Celsius. And T2 is 3.5 degrees Celsius. So if I go back and look at that, that should make sense. I come in here at minus 10. T2 is 3.5, so I've actually heated my air up by about 13 degrees, which is pretty substantial, right? That's 13 degrees of temperature rise I don't have to do in my furnace. If I look at my ethylene glycol, it's going to come in here at about 17 degrees Celsius, and it's going to leave here at about minus 2 degrees Celsius, right? So that's when it cools down, and then over here it's going to go in at minus 2 and warm up to 17 degrees Celsius. So that's my runaround loop, right? That's how this all works. I can do a few different things to sort of look at the solution and understand it. One thing is, just stepping back, if I consider this runaround loop as a heat exchanger, right, not as two individual heat exchangers, but as one heat exchanger, and sort of ignore what's going on inside of it, I can define an effectiveness for the runaround loop, right? So the effectiveness for the runaround loop is what's the rate of heat transfer from this exhaust air to the ventilation air, right? And then what's the maximum possible rate of heat transfer, which would be the capacitance rate of the air times TH_in, which is 25, minus TC_in, which is minus 10. Right, so that's the overall effectiveness of the runaround loop. And if I calculate that overall effectiveness, which I did down here, I find that the overall effectiveness of the runaround loop is 38%. So I've made a 38% effective heat exchanger by combining two 70% effective heat exchangers, if you want to think about it that way. Some interesting parametric studies that you can do that sort of show what heat exchanger problems always show is that you want to make your heat exchanger bigger, but not too big. You want to pump as much. So in this case, let's look at the ethylene glycol mass flow rate or the UA of these heat exchangers. And it's pretty easy to come over here and just comment out the ethylene glycol and run it and see what the let's look at T2. See what the see what the temperature entering the air, the building does. And if you look at that, what you'll find is as you increase the ethylene glycol flow rate, the temperature gets better and better, warmer and warmer. But at some point, you hit a land of diminishing returns, and so you're paying for pumping power out here that isn't really doing you any good, right? If you do the same thing for the conductance, you find the same kind of behavior, right? This is T2, this is conductance. Down here, it really pays to make your heat exchanger bigger, but at some point you hit this knee, and if you're out here, you can make your heat exchanger twice as big, and you really haven't impacted the economics of your system at all, right? You made your heat exchanger twice as big, you went from 20 to 40, but your temperature of the air going into the building only went up by a fraction of a degree. You wouldn't want to do that. Whereas down here, sure, making your heat exchanger twice as big is really important. And that's something we'll talk about here when we start talking about how effectiveness NTU solutions behave. And one thing you'll find is that as you get to NTUs around 2 or 3, that's always where you get this region of diminishing returns, right? So if I were to plot this T2 as a function of NTU of either of those two heat exchangers, you're going to find that around 2 or 3 is where I start to really lose any benefit of making it any bigger, right? And that's kind of a rule of thumb that you look at when you're designing heat exchangers is, am I designing a heat exchanger that has an NTU of 5? Because if so, that's kind of weird, right? It's you're not doing that much better at 5 than you would have done at 4. Or if I'm designing a heat exchanger that has an NTU of 0.1, I'm way down here. It seems to me like I should make it bigger than that. Like, going from 0.1 to 0.2 really helps a lot. So why wouldn't I do that? So this is just kind of a sanity check you can do. You can see with this design, I'd have to put in actual economic metrics to do a real design. But just looking at this curve, I want to be in this range here where I'm making my heat exchanger big, but not too big, right? So that's what we'll do next time is we'll finish up heat exchangers by looking at how these correlations actually behave. And then we'll move on to the last topic of the semester, which is radiation. So we'll talk a little bit about radiation.